terminus melts back faster than the rate at which ice reaches the terminus. Typically, the Ella ascends to a higher elevation as more of the glacier undergoes melting. In Glacier Bay, Alaska, glaciers have retreated over 100 kilometers in the past 200 years. Near the terminus, newly exposed rock is bare and lifeless. A few kilometers from the glacier, where the ground has been exposed for a few decades, lichens grow on otherwise bare rock, while mosses and dwarf fireweed can survive on thin soils formed in sheltered cracks where seabird droppings have mixed with windblown silt. Near the head of Glacier Bay, which deglaciated 200 years ago, tidal currents and ocean storms have washed enough sediment over the exposed bedrock to create a thicker soil capable of supporting a spruce hemlock rain forest. In equatorial and temperate regions, glaciers commonly terminate at an elevation of 3,000 meters or higher. However, in a cold, wet climate, a glacier may extend into the sea, where giant chunks of ice break off, forming icebergs. The largest icebergs in the world are those that break away from the Antarctic ice shelf. Between the years 2000 and 2002, 2 plates of ice the size of Connecticut and at least one the size of Rhode Island broke free from the West Antarctic ice sheet and floated into the Antarctic Ocean. In 2010, a 78-kilometer-long iceberg with a surface area greater than that of Massachusetts broke off of the terminus of the Mertz Glacier in Antarctica. In 2012, scientists analyzing 40 years' worth of satellite imagery from the ice shelf in West Antarctica reported that large portions of the ice shelf are slowly beginning to break away from the continent. If this breakaway continues, it will lead to the formation of more very large icebergs. Glacial erosion bedrock at the base and sides of a glacier may have been fractured by tectonic forces, frost wedging, or pressure release fracturing. Moving glacial ice commonly will dislodge and pluck individual boulders from such fractured bedrock. The plucked boulders are then transported downslope as clasts either within or at the base of the glacier. Ice is viscous enough to pick up and carry particles of all sizes, from house-sized boulders to clay-sized grains. Thus, glaciers erode and transport huge quantities of rock and sediment. Ice itself is not abrasive to bedrock, because it is too soft. However, rocks embedded in the ice scrape across bedrock, gouging deep, parallel grooves and scratches called glacial striations. When glaciers melt and striated bedrock is exposed, the markings show the direction of ice movement. Geologists measure the orientation of glacial striations and use them to map the flow directions of ancient glaciers. Erosional landforms created by alpine glaciers. Let's take an imaginary journey through a mountain range that was glaciated in the past but is now mostly ice-free. We start with a helicopter ride to the summit of a high, rocky peak. Our first view from the helicopter is of sharp, jagged mountains rising steeply above smooth, rounded valleys carved by glaciers. We've already seen that mountain streams in unglaciated regions commonly erode downward into their beds, cutting steep-sided, V-shaped valleys. A glacier, however, is not confined to a narrow stream bed, but instead extends across the valley bottom and commonly fills the entire valley itself. As a result, the glacier scours the sides of the valley as well as the bottom, carving a broad, rounded U-shaped valley. We land on one of the peaks and step out of the helicopter. Beneath us, a steep cliff drops off into a scoop-shaped depression in the mountainside called a cirque. A small glacier at the head of the cirque reminds us of the larger mass of ice that existed in a colder, wetter time. To understand how a glacier creates a cirque, imagine snow accumulating and a glacier forming on the side of a mountain. As the ice flows down the mountainside, it erodes a small depression that grows slowly as the glacier moves. With time and additional erosion, the depression deepens, causing the cirque walls to become steeper and higher. The glacier carries the eroded rock from the cirque to lower parts of the valley. When the glacier finally melts, it leaves behind a steep-walled, rounded cirque. Streams and lakes are common in glaciated mountain valleys. As a cirque forms, the glacier may erode a depression into the bedrock beneath it. When the glacier melts, this depression can fill with water, forming a small lake, or tarn, nestled at the base of the cirque. If we hike down the valley below the high cirques, we may encounter a series of paternoster lakes. The term paternoster refers to a string of rosary beads connected by a string. Paternoster lakes are formed as a glacier erodes a sequence of small basins that later fill with water when the glacier recedes. The lakes are connected by a stream that commonly features rapids and waterfalls. If glaciers erode 3 or more cirques into different sides of a peak, they will create a steep, pyramid-shaped rock summit called a horn. The Matterhorn in the Swiss Alps is a famous horn. Similarly, two alpine glaciers flowing down opposite sides of a mountain ridge will erode both sides, forming a sharp, narrow rib of rock called an arete. When the glaciers melt, the arete will form a drainage divide that separates the two adjacent valleys or cirques. Looking downward from our peak, we may see a waterfall pouring from a small, high valley into a larger, deeper one. A small glacial valley lying high above the floor of the main valley is called a hanging valley. The famous waterfalls of Yosemite Valley in California cascade from hanging valleys. A hanging valley forms where a small tributary glacier joined a much larger one. The tributary glacier eroded a shallow valley, while the massive main glacier gouged a deeper one. When the glaciers melted, they exposed an abrupt drop where the small valley joins the main valley. Deep, narrow inlets called fjords extend far inland on many high-latitude seacoasts. Most fjords are glacially carved valleys that were later flooded by encroaching seas as the glaciers melted. Erosional landforms created by a continental glacier erodes the landscape just as an alpine glacier does. However, a continental glacier is considerably larger and thicker and is not confined to a valley. As a result, it covers a large area that can include entire mountain ranges. The most recent continental glacier in North America stretched from beyond the present New England coastline westward to the high plains of the Dakotas and eastern Montana. Glacial deposits in the 1800s, geologists recognized that the large deposits of sand and gravel found in the Alps and other places had been transported from distant sources. A popular hypothesis at the time explained that this material had drifted in on icebergs during catastrophic floods. The deposits were called drift after this inferred mode of transport. Today we know that continental glaciers covered vast parts of the land only 10,000 to 20,000 years ago and that these glaciers carried and deposited drift. Although the term drift is a misnomer, it remains in use. Now geologists define drift as an all-embracing term for sediments of glacial origin, no matter how the sediments were deposited. Drift is divided into two categories. Till was deposited directly by glacial ice. Stratified drift refers to sediments first carried by a glacier but ultimately deposited by glacial meltwater. Landforms composed of till ice is so much more viscous than water that it carries a wide range of particle sizes. When a glacier melts, it deposits particles of all sizes, from fine clay to huge boulders, in an unsorted, unstratified mass. Cobbles and boulders carried by a glacier often show scratches or grooves caused by the slow grinding of one clast against another during transport within the ice. However, gravel carried by a glacier is not rounded in the same way as gravel carried by a stream, because the clasts in a glacier do not undergo numerous collisions during transport. Therefore, if you find rounded gravel in a till, it probably became rounded by a stream before the glacier picked it up. In some places, large boulders or smaller-sized rock fragments consisting of a rock type different from the bedrock in the immediate vicinity can be found in glaciated country. Rocks of this type are called erratics. Most were transported to their present locations by a glacier. The origins of erratics can be determined by exploring the terrain in the direction the glacier came from until the parent rock is found. Some erratics were carried 500 or even 1,000 kilometers from their points of origin and provide clues to the movement of glaciers. In some cases, individual mineral grains known to come from rare types of parent rocks can be used to determine the location of the parent rocks, as with the discovery of Canadian diamonds discussed in the Digging Deeper box. Moraines. A moraine is a mound or a ridge of till. Think of a glacier as a giant conveyor belt. An old-fashioned airport conveyor belt simply carries suitcases to the end of the belt and dumps them in a pile. Similarly, a glacier carries sediment and deposits it at its terminus. If a glacier is neither advancing nor retreating, its terminus may remain in the same place for years. During that time, sediment accumulates at the terminus to form a ridge called an end moraine. An end moraine that forms when a glacier is at its greatest advance, before beginning to retreat, is called a terminal moraine. If warmer conditions prevail, the glacier recedes. If the glacier then stabilizes again during its retreat and the terminus remains in the same place for a sufficient amount of time, a new end moraine, called a recessional moraine, forms upslope of the terminal moraine. In some cases, multiple recessional moraines are deposited upslope of the terminal moraine. When a glacier recedes steadily, till is deposited in a relatively thin layer over a broad area, forming a ground moraine. Ground moraines fill old stream channels and other low spots. Often this leveling process disrupts drainage patterns. Many of the swamps in the northern Great Lakes region and northern New England lie on ground moraines formed when the most recent continental glaciers receded. End moraines and ground moraines are characteristic of both alpine and continental glaciers. An end moraine deposited by a large alpine glacier may extend for several kilometers and be so high that even a person in good physical condition would have to climb for an hour to reach the top. Moraines may be dangerous to hike over if their sides are steep and the till is loose. Large boulders are mixed randomly with rocks, cobbles, sand, and clay. A careless hiker can dislodge boulders and send them tumbling to the base. The most recent Pleistocene continental glaciers reached their maximum extent about 18,000 years ago. Their terminal moraines record the southernmost extent of those glaciers. In North America, the terminal moraines lie in a broad, undulating front extending across the northern United States. Enough time has passed since the glaciers retreated that soil has formed on the till and vegetation now covers the terminal moraines. When an alpine glacier moves downslope, it erodes the valley walls as well as the valley floor. Additional debris falls or slides down from the valley walls and accumulates directly on mountain glaciers and their margins. Thus, large sediment loads are carried along the lateral edges of glaciers. When the glacier retreats, this sediment is left behind as a ridge of till called a lateral moraine. If two alpine glaciers converge, their lateral moraines merge into the middle of the resulting larger glacier. This till forms a visible dark stripe on the surface of the ice, called a medial moraine. Drumlins elongate parallel hills, called drumlins, are common across the northern United States and are well exposed across parts of upstate New York, Michigan, Wisconsin, and Minnesota. Drumlin is from the Old Irish for back or ridge, and each one looks like a whale swimming through the ground, with its humped back in the air. An individual drumlin is typically about 1 to 2 kilometers long and about 15 to 50 meters high. Drumlins usually occur in clusters, called drumlin fields. Drumlins typically consist of multiple layers of till that are roughly parallel to the drumlin's upper surface but that also show erosion on the upstream side. A recent study of drumlins in Iceland shows that they are formed near the terminus of a glacier by multiple surges of the ice. According to this study, crevasses in the ice concentrate piles of sediment directly below, along the bed of the glacier. As the glacier surges, the ice sculpts the pile of till into a teardrop shape in which the steeper upstream side is partly eroded and the till is carried to the downstream side, where it is deposited to form the more gently sloping tail of the drumlin. With each successive surge of the glacier, another layer of till is plastered to the outer edge of the drumlin and shaped by the glacial movement. Landforms consisting of stratified drift because glacier erodes. Great amounts of sediment, subglacial streams, and outwash streams are typically laden with silt, sand, and gravel. Most of this sediment is deposited beyond the glacier terminus as outwash. Outwash streams carry such a heavy sediment load that they often become braided, flowing in multiple channels. Over time, outwash deposited in a valley will form a broad, gently sloping valley floor called a braid plain. Outwash deposited in front of continental glaciers forms a larger outwash plain. During summer, melting of snow and ice causes streams to form on the surface of a glacier. Many of these streams flow off the front or sides of the glacier, while others plunge into tunnels in the ice and flow downward, ultimately to become part of a subglacial stream. Subglacial streams not only can erode the sediment bed below the glacier but they also can carve upside-down channels into the base of the ice. These channels in the ice can become filled with well-sorted stratified drift that forms a long, sinuous deposit called an esker when the glacier melts. Eventually, subglacial streams will reach the end of the glacier and emerge from beneath its terminus as an outwash stream. Commonly, large pieces of glacial ice will separate from the main glacier during glacial retreat, forming stagnant ice that is no longer connected to the glacier's conveyor belt ice delivery system. Sediment from outwash streams flowing around the stagnant ice will accumulate in a pile called a kame. As large blocks of stagnant ice melt, they leave behind depressions, called kettles, that often fill with water. Kames and kettles commonly occur together, forming kame and kettle topography that is typical of stagnant ice associated with a retreating glacier. Large volumes of glacial meltwater can temporarily collect in lakes that form downslope from a glacier. Proglacial lakes form immediately in front of a retreating glacier and usually are dammed by the glacier's terminal moraine. In addition, large pluvial lakes can form in topographic basins that do not have an outflow. During the Pleistocene, several such pluvial lakes formed in the topographic basins of western Utah, Nevada, and southern Idaho. The Great Salt Lake in Utah is a remnant of a once larger pluvial lake called Glacial Lake Bonneville. Because kames, eskers, and sediment accumulating in glacial lakes are not deposited directly by ice, they typically show sorting and sedimentary bedding, which distinguishes them from unsorted and unstratified till. In addition, transport by streams usually rounds clasts deposited in these environments, in contrast with the more angular clasts typical of glacial till. The Pleistocene glaciation geologists have found terminal moraines extending across all high-latitude continents. By studying those moraines, as well as lakes, eskers, outwash plains, and other glacial landforms, geologists have concluded that massive glaciers once covered large portions of the continents, altering Earth systems. A time when alpine glaciers descend into lowland valleys and continental glaciers advance across the land surface at high latitudes is called a glaciation. During a glaciation, glaciers several kilometers thick and thousands of kilometers across can spread across the land surface. Beneath this burden of ice, the continents sink deeper into the asthenosphere. The ice erodes rock and soil and deposits it elsewhere, completely altering the landscape. Geologic evidence shows that Earth has been warm and relatively ice-free for at least 90% of the past 1 billion years. However, at least 6 major glaciations occurred during that time. Each one lasted from 2 to 10 million years and was separated in time from relatively ice-free interglacial periods. The most recent glaciations have taken place during the Pleistocene epoch and collectively are called the Pleistocene glaciation. The Pleistocene glaciation began about 2 million years ago in the northern hemisphere, although evidence of an earlier beginning has been found in the southern hemisphere. However, Earth was not glaciated continuously during the Pleistocene epoch. Instead, climate fluctuated and continental glaciers grew and then melted away several times. During the most recent interglacial period, the average temperature was about the same as it is today, or perhaps a little warmer. Then, high-latitude temperature dropped at least 15 degrees Celsius, causing the ice to advance. Many climate models indicate that the conditions leading to the Pleistocene glaciation still exist and that continental ice sheets may advance again. Causes of the Pleistocene glacial cycles for reasons that are poorly understood. Prior to 2 million years ago, Earth's climate had been cooling for tens of millions of years, and then something happened to push the planet over a climate threshold and plunge it into a glaciation. An increase in volcanic ash 2 million years ago coincided closely with a dramatic increase in sediment grains that showed glacial markings. Although volcanic dust may have triggered the onset of the Pleistocene glaciation, no such event seemed to be associated with the repeated growth and melting of glaciers that characterized the glacial interval. Instead, scientists have found that slight, periodic variations in Earth's orbit and orientation relative to the Sun coincided with glacial expansion and shrinking during the Pleistocene glaciation. In the 19th century, astronomers recognized 3 periodic variations in Earth's orbit and spin axis. 1. Earth's orbit around the Sun is elliptical rather than circular. The shape of the ellipse is called eccentricity. The more elliptical the orbit, the more eccentric it is said to be. Earth's orbit eccentricity varies in a regular cycle lasting about 100,000 years. 2. The tilt, or angle of Earth's axis, is currently about 23.5 degrees with respect to a line perpendicular to the plane of its orbit around the Sunday. The tilt oscillates by about 2 degrees on about a 41,000 year cycle. 3. Earth's axis, which now points directly toward the North Star, circles like that of a wobbling top. This circling, called precession, completes a full cycle every 26,000 years. These changes affect both the total solar radiation received by Earth and the distribution of solar energy with respect to latitude and season. Seasonal changes in sunlight reaching higher latitudes can reduce summer temperatures. If summers are cool and short, winter snow and ice persist, leading to the growth of glaciers. Early in the 20th century, a Yugoslavian astronomer, Milutin Milankovic, calculated that the orbital variations generate alternating cool and warm climates in the mid-latitudes and higher latitudes. Moreover, the timing of the calculated cooling coincided with that of Pleistocene glacial advances. Therefore, he concluded that orbital variations caused Pleistocene glacial cycles. Modern calculations indicate that orbital cycles by themselves are not sufficient to cause glaciers to advance and retreat. Instead, orbital cycles disturb other Earth systems, which in turn cause additional cooling. Thus, a relatively small initial disturbance is amplified to cause a major climate change. In one recent study, researchers calculated that orbital variations probably caused high-latitude climate to cool enough to kill vast regions of Pleistocene northern forest. Forests control climate by absorbing solar energy and warming the atmosphere. When the forests died, more solar energy reflected back out to space. This loss of solar energy caused Earth to cool even more, and the glaciers advanced. Because ice reflects more solar radiation back into space, a feedback process developed in which the growing glaciers accelerated global cooling. In this way, variations in Earth's orbit could have altered the biosphere enough to trigger a feedback that led to global cooling and a major glacial advance. Effects of Pleistocene continental glaciers. At its maximum extent about 18,000 years ago, the most recent North American ice sheet covered 10 million square kilometers, most of Alaska, Canada, and parts of the northern United States. At the same time, alpine glaciers flowed from the mountains into the lowland valleys. The erosional features and deposits created by these glaciers dominate much of the landscape of the northern United States. Today, terminal moraines form a broad band of rolling hills from Montana across the Midwest and eastward to the Atlantic Ocean. Kettle lakes or lakes dammed by moraines are abundant in northern Minnesota, Wisconsin, and Michigan, while drumlins dot the landscape across much of the northern Midwest. Ground moraines, outwash, and wind-blown glacial silt, or loess cover much of the northern Great Plains. These deposits have weathered to form the fertile soil of North America's breadbasket. Sea level changes with glaciation. When glaciers grow, they accumulate water that would otherwise be in the oceans, and sea level falls. When glaciers melt, sea level rises again. When the Pleistocene glaciers reached their maximum extent roughly 18,000 years ago, global sea level fell to about 130 meters below its present elevation. As submerged continental shelves became exposed, the global land area increased by 8%. When the ice sheets melted, most of the water returned to the oceans, raising sea level again. At the same time, portions of continents rebounded isostatically as the weight of the ice was removed. Thus, while the rising seas submerged some coastlines, others rebounded more than sea level rose, causing the sea to retreat. For example, former beaches in the Canadian Arctic now lie tens of meters to a few hundred meters above the sea. Snowball Earth, the greatest glaciation in Earth's history. Research suggests that at least twice, and perhaps as many as 5 times in late Precambrian time between 800 and 550 million years ago, massive ice sheets completely covered all continents and the world's oceans froze over, even at the equator, entombing the entire globe in a 1-kilometer thick shell of ice. This glaciation, called Snowball Earth by the researchers who discovered it, contrasts sharply with the Pleistocene glaciation, when ice covered just a third of the continents and only the polar seas froze over. The main evidence for the Precambrian Snowball Earth is based on a unique rock called tillite. Recall that till consists of an unsorted mixture of boulders, silt, and clay that was deposited by a glacier. Pleistocene tills are made of loose sediment that can be easily dug up with a shovel. Tillite, however, is hard, solid rock that in every other respect resembles the Pleistocene tills. Simply put, tillite is till that was deposited by glaciers so long ago that it has become cemented into hard rock. Researchers have found at least 2 thick layers of tillite between 750 and 580 million years old on almost every continent. Recall that continents have moved around Earth through geologic time. Other types of evidence show that some of the continents lay at the equator when the tillites formed. Other continents were nearer to the poles at the same time, showing that the glaciations were global in scope. The Earth's disappearing glaciers are now shrinking in more places and at more rapid rates than at any other time since scientists began keeping records. In 2003, during a single, hot summer in Europe, 10% of the glacial ice in the Alps melted. Scientists point out that this accelerated loss of glacial ice coincides with an increase in atmospheric carbon dioxide levels of about 50% in the past century, and they suggest that the melting may be one of the first symptoms of human-caused global warming. Alpine glaciers reflect these changes in a highly visible way. The larger glaciers in Glacier National Park, Montana, have shrunk to a third of their size since 1850, and they continue to melt away today. Many of the smaller glaciers have disappeared completely. Since 1850, the number of glaciers in the park has decreased from 150 to fewer than 25 in 2010. One computer model predicts that all of the glaciers will be gone from the park by 2030 if global temperatures continue to rise as predicted, though other models suggest that this prediction is overstated. As demonstrated in Table 13.1, significant loss of glacial ice volumes through melting is a global phenomenon. In some instances, ice disintegration has been particularly dramatic. For example, half of Alaska's Columbia Glacier melted between 1980 and 2011, and the glacier currently releases about 5 cubic kilometers of meltwater into Prince William Sound every year. Elsewhere, scientists predict that glaciers in the European Alps will be all but gone by 2050. Global climate changes do not occur uniformly around the globe. The North Polar regions are warming faster than the average rate for all of Earth, and this warming is having a profound effect on Arctic sea ice. During the winter, Arctic sea ice covers an area about the size of the United States, though it is rapidly shrinking in size and thickness. Ice thickness measurements during 2011 and 2012 indicate that the summer ice pack those years was the thinnest, least extensive on record, and many scientists predict that Arctic summer sea ice will completely disappear in the next few decades. Such a loss would greatly increase the amount of solar energy that is absorbed by the Arctic Ocean, potentially accelerating global warming. Ice shelves are thick masses of ice that are floating in the ocean but are connected to glaciers on land. They gain ice by flow from the land glaciers and lose ice by melting and when large chunks break off and float into the ocean as icebergs. Most of Earth's ice shelves surround Antarctica. Ice shelves respond to rising temperature more sensitively than glaciers do. Since 1974, 7 Antarctic ice shelves have shrunk by a total of 13,500 square kilometers. These ice shelves are described further in Chapter 21. The melting of the Arctic and Antarctic ice has profound effects for the planet. This melting contributes to the rise in sea level, and the freshwater flowing into the ocean may ultimately alter ocean currents and global climate. Chapter 14. Deserts and Wind. Introduction. Earth's continents are classified into climate zones based primarily on precipitation and temperature. In turn, climate determines the communities of plants and animals that live in a region. A desert is any region that receives less than 25 centimeters of rain per year and consequently supports little or no vegetation. Most deserts are surrounded by semi-arid zones that receive 25 to 50 centimeters of annual rainfall, more moisture than a true desert but less than adjacent regions. Deserts cover 25% of Earth's land surface outside of the polar regions and make up a significant part of every continent. If you were to visit the great deserts of Earth, you might be surprised by their geologic and topographic variety. You would see coastal deserts along the beaches of Chile, shifting dunes in the Sahara, deep, red sandstone canyons in southern Utah, stark granite mountains in Arizona, and bitter cold polar deserts with a few lichens clinging tenaciously to the otherwise barren rock. The world's deserts are similar only in that they all receive scant rainfall. Why do deserts exist? Rain and snow are unevenly distributed over Earth's surface. For example, Mount Waialaeal, Hawaii, one of the wettest places on Earth, receives an average of 1,168 centimeters of rain annually. In contrast, 10 years or more may pass between rains or snowfalls in the Atacama Desert of Peru and Chile. Several factors, including latitude, mountains, and atmospheric circulation, control rainfall patterns and therefore the global distribution of deserts and semi-arid lands. Latitude. The sun shines most directly overhead near the equator, warming air near Earth's surface. The air absorbs moisture from the equatorial oceans and rises because it is warmer, and therefore less dense, than surrounding air. Rising air cools as pressure decreases. But cool air cannot hold as much water as warm air, so the water vapor condenses and falls as rain. For this reason, vast tropical rain forests grow near the equator. This rising equatorial air, which is now drier because of the loss of moisture, flows both northward and southward at high altitudes. There the air cools, becomes denser, and sinks back toward Earth's surface at about 30 degrees north and south latitudes. As the air falls, it is compressed and becomes warmer, which enables it to hold more water vapor. As a result, water evaporates from the land surface into the air. Because the sinking air absorbs water, the ground surface is dry and rainfall is infrequent. Thus, many of the world's largest deserts lie at about 30 degrees north and south latitudes. Mountains, rain shadow deserts. When moisture-laden air flows over a mountain range, it rises. As the air rises, it cools and its ability to hold water decreases. As a result, the water vapor condenses into rain or snow, which falls as precipitation on the windward side and on the crest of the range. The drier, cool air continues down the leeward side of the mountain, compressing and warming as it descends. This warm, dry air creates an arid zone called a rain shadow desert on the leeward side of the range. In this way, tectonic forces, which produce mountains, affect very long-term rainfall patterns. In turn, as we learned in Chapter 10, flowing water will weather rock, forming soil and defining the local environmental conditions on which various ecosystems exist. Thus we encounter yet another example of interacting Earth systems, because the building of a mountain range alters rainfall and ultimately defines the types of ecosystems that characterize a region. Coastal and interior deserts. Because most evaporation occurs over oceans, one might expect that coastal areas would be moist and climates would become drier with increasing distance from the sea. This is generally true, but a few notable exceptions exist. The Atacama Desert along the west coast of South America is so dry that portions of Peru and Chile often receive no rainfall for a decade or more. Cool ocean currents flow along the west coast of South America. When the cool marine air encounters warm land, the air is heated and expands. As it warms, the air absorbs moisture from the ground, creating a coastal desert. The Gobi Desert is a broad, arid region in Central Asia. The center of the Gobi lies at about 40 degrees north latitude, and its eastern edge is a little more than 400 kilometers from the Yellow Sea. As a comparison, Pittsburgh, Pennsylvania, lies at about the same latitude and is 400 kilometers from the Atlantic Ocean. If latitude and distance from the ocean were the only factors, these regions would have similar climates. However, the Gobi is a barren desert and western Pennsylvania receives enough rainfall to support forests and rich farmland. The Gobi is bounded by the Tibetan Plateau to the south and the Altai and Tian Shan mountain ranges to the west, which shadow it from the prevailing winds. In contrast, winds carry abundant moisture from the Gulf of Mexico, the Great Lakes, and the Atlantic Ocean to western Pennsylvania. Thus, in some regions deserts extend to the seashore, whereas in other regions the interior of a continent is humid. The climate at any particular place on Earth results from a combination of many factors. Latitude and proximity to the ocean are important, but complex interactions involving the direction of prevailing winds, the direction and temperature of ocean currents, and the positions of mountain ranges also control climate. Water in deserts. Although rain and snow rarely fall in deserts, water plays an important role in these dry environments. Water can reach a desert from three sources. Streams flow from adjacent mountains or other wetter regions, bringing surface water to some desert areas. Groundwater may also flow from a wetter source to an aquifer beneath a desert. Finally, rain and snow fall occasionally on deserts. Thus, even in the driest places on Earth, the hydrosphere and geosphere interact. Vegetation is sparse in most deserts because of the limited water supply. Much bare soil is exposed, unprotected from erosion. As a result, rain can easily erode desert soils, and flowing water is an important factor in the evolution of desert landscapes. Desert streams. Large rivers flow through some deserts. For example, the Nile River flows through North African deserts and the Colorado River crosses the arid southwestern United. Figure 14.4. The Colorado River flows from the Rocky Mountains through the arid southwestern United States. Desert rivers receive most of their water from wetter, mountainous regions bordering the arid lands. In a desert, the water table is commonly deep below a streambed, so that water seeps downward from the stream into the ground. As a result, many of the smaller desert streams flow only for a short time after a rainstorm, or during the spring when winter snows are melting, before their water seeps below the streambed. A streambed that is dry for most of the year is called a wash. Desert lakes. In humid climates, the water table is relatively shallow, and groundwater can flow from saturated sediment or rock in the subsurface directly into a lake. In this situation, the lake surface projects into the subsurface as the water table, which separates the zone of saturation below from the zone of aeration above. In contrast, many desert lakes lie well above the water table. During the wet season, rain and streams may fill a desert lake. Whereas some desert lakes are drained by outflowing streams, most lose water only by evaporation and seepage. In large desert lakes such as the Great Salt Lake in Utah and the Dead Sea in Israel and Jordan, evaporation has caused the remaining lake water to become very saline and has even resulted in the precipitation of salt within the lake basin. In smaller desert lakes, inflowing streams may cease to flow during the dry season, causing the lake to dry up completely due to evaporation and seepage. This kind of intermittent desert lake is called a playa lake, and the dry lake bed is called a playa. Recall from Chapter 11 that streams and groundwater contain dissolved salts. When this slightly salty water fills a desert lake and then evaporates, the ions are left behind and salt minerals precipitate on the playa. Over many years, economically valuable mineral deposits, such as those of Death Valley, may accumulate flash floods bedrock or tightly. Compacted soil covers the surface of many deserts, and little vegetation is present to help absorb moisture. As a result, rainwater runs over the surface and collects in gullies and washes. During a rainstorm, a dry streambed may fill with water so rapidly that a flash flood, a brief, intense local flood, occurs. Occasionally, novices to desert camping pitch their tents in a wash, where they find soft, flat sand to sleep on and shelter from the wind. However, if a thunderstorm occurs upstream during the night, a flash flood may fill the wash with a wall of water mixed with rocks and boulders, creating disaster for the campers. By mid-morning of the next day, the wash may contain only a tiny trickle, and within 24 hours it may be completely dry again. When rainfall is unusually heavy and prolonged, runoff flowing across a sloping desert soil will rapidly pick up sediment and evolve into a slurry-like debris flow. As its consistency thickens with the addition of the sediment, a debris flow can become powerful enough to carry large boulders and substantially damage or destroy buildings in its path. Some of the most expensive homes in Phoenix, Arizona, and other desert cities are built on alluvial fans and steep mountainsides, where they afford good views but are at risk from the effects of debris flows during wet years. Pediments and bajadas. Recall from Chapter 11 that when a steep, flooding mountain stream empties into a flat valley, the water slows abruptly and deposits most of its sediment at the mountain front, forming an alluvial fan. Although fans form in all climates, they are particularly conspicuous in deserts. A large fan may be several kilometers across and rise a few hundred meters above the surrounding valley floor. If the mouths of several canyons are spaced only a few kilometers apart, the alluvial fans extending from each canyon may merge. A bajada is a broad, gently sloping depositional surface formed by merging alluvial fans and extending into the center of a desert valley. Typically, the fans merge incompletely, forming an irregular surface that follows the mountain front for tens of kilometers. Over millions of years, the alluvial sediment forming the bajada may accumulate to a thickness of several kilometers. A pediment is a broad, gently sloping erosional surface. Pediments commonly form along the front of desert mountains, because tectonic uplift results in erosion and, hence, development of the pediment. The surface of a pediment is covered with a thin veneer of gravel that is in the process of being transported from the mountains, across the pediment, to the bajada. Together, a pediment and bajada form a smooth surface from the mountain front to the valley center, Figure 14. 11. The surface steepens slightly near the mountains, so it is concave up. To distinguish a pediment from a bajada, you would have to dig or drill a hole. If you were on a pediment when making the hole, you would strike the eroded rock or sediment after only a few meters on a bajada, in contrast, hundreds or even thousands of meters of recent gravel would cover the older rock or sediment. 2. American deserts. The Colorado Plateau. The Colorado Plateau covers a broad region encompassing portions of Utah, Colorado, Arizona, and New Mexico. During the past billion years of Earth's history, this region has been alternately covered by shallow seas, deserts, and broad alluvial plains with rivers and lakes. Sediment accumulated in these environments and slowly lithified to become flat layers of sedimentary rock. Tectonic forces later uplifted the lithified flat layers of rock over a broad region, forming the Colorado Plateau. Today, much of the Colorado Plateau receives less than 25 centimeters of rainfall per year. As the plateau rose, the Colorado River cut downward through the bedrock to form the 1.6 kilometer deep Grand Canyon and its tributary canyons. The modern Colorado River receives most of its water from snowmelt and rain in the high Rocky Mountains east and north of the plateau, and the river then flows southwestward through the heart of the Great Desert to the Gulf of California, in northern Mexico, where it empties. In addition to water, the Colorado River and its tributaries transport much sediment toward the Gulf of California. Uplift of the Colorado Plateau causes these streams to erode downward into bedrock. This downcutting continues until a resistant layer is reached. As discussed in Chapter 11 in section on downcutting and base level, such a resistant layer will form a temporary base level. Once the base level is reached, the stream begins to erode laterally, widening the canyon by undercutting its walls and causing the rock to collapse along vertical joints. Continued lateral erosion and removal of the sediment by the river forms a relatively level plain with flat-topped mesas and buttes that rise above it as erosional remnants that are left behind. The flat tops of mesas and buttes usually form on a bed of sandstone or other sedimentary rock that is relatively resistant to erosion. These resistant upper layers temporarily protect the landforms from erosion, somewhat like a roof protects a building, although continued lateral erosion of the sides of the landform ultimately causes it to be removed. In many cases across the Colorado Plateau, extensive lateral erosion above a temporary base level leaves spectacular pinnacles or spires, isolated remnants of once continuous rock layers that the streams have all but completely eroded away. The huge volumes of sediment that are produced through this lateral erosion are transported away from the region by streams and ultimately are redeposited near the shoreline as part of a delta or carried further offshore to be deposited on a deepwater submarine fan. We will explore deltas and submarine fans in Chapter 15. This style of lateral erosion to a temporary base level produces a wide variety of spectacular landforms that are common in the desert west where flat-lying layered sedimentary rocks are exposed at the surface. The largest of these features is a plateau, a region of fairly flat land that has been uplifted by tectonic forces and usually is made of relatively flat-lying sedimentary or volcanic rock. The Colorado Plateau is a good example, as it consists of relatively flat-lying sedimentary rocks that have been uplifted to elevations of several kilometers. The Colorado Plateau is surrounded by the North American Basin and Range Extensional Province, and this extension is slowly nibbling away at the margins of the plateau. Other plateaus include the Columbia River Plateau, formed by the extensive flat-lying basalt flows of Cenozoic age, and the Tibetan Plateau, a large feature in Central Asia resulting from the continent-continent collision between India and Asia. See Chapter 9. Smaller than a plateau is a flat-topped mountain shaped like a table and called a mesa, Spanish for the word table. A butte is also a flat-topped mountain, smaller and more tower-like than a mesa, and characterized by steep cliff faces. Even smaller is a spire, a single tower with a pointy top. Mesas, buttes, and spires are all erosional landforms that are common in the Colorado Plateau. Death Valley and the Great Basin. Death Valley lies in the rain shadow of the high Sierras. In California, the deepest part of the valley is 86 meters below sea level. It is a classic rain shadow desert, receiving a scant 5 centimeters of rainfall per year. The mountains to the west receive abundant moisture, and during the winter rainy season and spring snowmelt, streams flow from the mountains into the valley, where a playa lake forms. On the Colorado Plateau, the Colorado River and its tributaries carry sediment away from the desert to the Gulf of California, leaving deep canyons. In contrast, streams flow into Death Valley from the surrounding mountains, but no streams flow out. Because Death Valley has no external drainage, the valley is filling with sediment eroded from the surrounding mountains. The sediment collects to form vast alluvial fans and bajadas. Stream water flows into a playa lake that dries up under the hot summer sun. Death Valley is just one small part of a vast desert region in the American West that has no external drainage. The Great Basin is a large desert region between the Sierra Nevada and the Rocky Mountains. Because there are no streams flowing out of the Great Basin, sediment is not removed and instead has accumulated to become thousands of meters thick. Like the Colorado Plateau, the Great Basin currently is being uplifted, but it is also being pulled apart by ongoing tectonics. This tectonic extension causes normal faults to form that downdrop the valleys and uplift the mountains of the Great Basin. As we discussed in Chapter 9, the downdropped valleys are called graben, and the uplifted mountains are called horsts. Desert streams have partially eroded the mountains and deposited sediment to form pediments, alluvial fans, and bajadas that today are very common in the Great Basin. With no streams carrying deposits out of the Great Basin, the mountains are drowning in their own sediment. Figure 14.14c, Wind, just as water from the hydrosphere, plays an important role. In the desert environment, moving air of the atmosphere also shapes and sculpts the desert landscape. When wind blows through a forest or across a prairie, the trees or grasses shield the soil from wind erosion. Water dampens the soil and binds particles together, further protecting it from wind erosion. In contrast, a desert commonly has little or no vegetation and rainfall, so wind erodes bare, unprotected desert soil. Wind erosion is not limited to deserts. Wind is an important agent of erosion wherever the wind blows over unvegetated soil. Wind-blown dunes of sand are common along seacoasts, where salty sea spray limits plant growth, and in regions recently left bare by receding glaciers. Wind erosion, called deflation, is a selective process. Because air is much less dense than water, wind is capable of moving only small particles, generally those sand-sized and finer. Imagine bare soil containing silt, sand, pebbles, and cobbles. When wind blows, it removes only the silt and sand, leaving the pebbles and cobbles behind to form a continuous armoring of stones called a desert pavement. A desert pavement prevents the wind from eroding additional sand and silt, even though this finer sediment may be abundant beneath the stony armor. Approximately 80% of the world's desert area is covered by a pavement of pebbles and cobbles, figure 14.15b, whereas only 20% is covered by sand. Transport and abrasion. Wind erosion is caused by sand-sized grains of sediment that are entrained in wind. When it is strong enough, wind can begin to roll and bounce sand grains across the ground surface. If the wind strengthens, some of the grains will be kicked upward, then carried downwind a short distance before falling back to the surface, in a process called saltation. The resulting trajectory of each grain is asymmetric, with a steeper ascent angle and a more shallow descent angle. When the wind is strong enough to cause many grains to saltate at one time, a saltation carpet is formed. Such wind-blown, saltating sand is abrasive and capable of eroding bedrock. In some cases where hard bedrock such as quartzite is exposed, wind-blown sand can polish the bedrock surface. Because saltation carpets form next to the ground surface, wind erosion usually is most intense close to the ground. In rare cases, oddly shaped temporary spires can result in which a thin rock pedestal supports a larger mass above. Eventually, such balanced rocks will collapse as the pedestal continues to be undercut. In contrast to sand-sized particles, smaller silt and clay-sized particles can be carried by wind for much longer distances. Large storms in the Sahara, for example, can carry small particles in suspension in the atmosphere for hundreds of miles before they settle back to the surface. Skiers in the Alps commonly encounter a thin layer of silt on the snow surface resulting from wind transport of fine sediment from the Sahara across the Mediterranean Sea. Dunes. A dune is an asymmetric mound or ridge of wind-deposited sand. As explained earlier, wind removes sand from the surface in many deserts, leaving behind a stony desert pavement. The wind commonly deposits such sand in a topographic depression or other place where the wind slows down. Dunes commonly grow to heights of 30 to 100 meters, and some giants exceed 500 meters. Most dunes are between about 100 meters and 1 kilometer across, although some dune ridges in the western Sahara are hundreds of kilometers long. The largest dune field on Earth is the Rub al Khali in Arabia, which covers 560,000 square kilometers, larger than the state of California. Most dune fields cover a few square kilometers. Dunes also form where glaciers have recently receded and along sandy coastlines. Glacial deposits consist of large quantities of bare, unvegetated sediment. A sandy beach is commonly unvegetated because sea salt prevents plant growth. As a result, both of these environments contain the essentials for dune formation, an abundant supply of sand and a windy environment with sparse vegetation. Most dunes are asymmetrical. Sand eroded by wind from the windward side of the dune saltates up to the dune crest. From there, the sand moves down the steep leeward dune face, called the slip face, as a series of small, tongue-like grain flow deposits before coming to rest as an inclined layer of sand. Typically, the slip face dips about 35 degrees from horizontal, the angle of repose for dry sand. The inclined layers of sand that result from this process form crossbeds that reflect the original slope of the dune slip face. Migrating dunes can overrun buildings and highways. For example, near the town of Winnemucca, Nevada, dunes advance across U.S. Highway 95 several times a year. Highway crews must remove as much as 4,000 cubic meters of sand to reopen the road. Engineers often attempt to stabilize dunes in inhabited areas. One method is to plant vegetation to reduce deflation and stop dune migration. The main problem with this approach is that desert dunes commonly form in regions that are too dry to support vegetation. Another solution is to build artificial windbreaks to create dunes in places where they do the least harm. For example, a fence traps blowing sand and forms a dune, thereby protecting areas downwind. Fencing is a temporary solution, however, because eventually the dune covers the fence and resumes its migration. In Saudi Arabia, dunes are sometimes stabilized by covering them with tarry wastes from petroleum refining. Types of sand dunes: wind speed and sand supply control the shapes and orientation of dunes. A Barkhan dune is one of 4 common types of dunes and forms in rocky deserts where there is a limited supply of sand. The center of the dune grows higher than the edges, but migrates forward more slowly, causing the dune to become crescent-shaped, with its tips pointing downwind. Barkhan dunes are not generally connected to one another but instead migrate independently. If sparse desert vegetation is present, the wind may form a small depression called a blowout. In a bare area among the desert plants, as sand is carried out of the blowout, it accumulates in a parabolic dune, the tips of which are anchored by plants on each side of the blowout. Parabolic dunes are common in moist semi-desert regions and along seacoasts, where sparse vegetation grows in the sand. In environments where sand is plentiful and evenly dispersed, it accumulates in long ridges called transverse dunes aligned perpendicular to the prevailing wind. If 2 different wind directions prevail throughout the year and both are of comparable magnitude, then long, straight longitudinal dunes can form. In portions of the western Sahara Desert, longitudinal dunes reach 100 to 200 meters in height and are as much as 100 kilometers long. Depending on the angle between the 2 prevailing wind directions, longitudinal dunes form either perpendicular or parallel to the average annual wind direction. Fossil dune sedimentary structures are common when sand dunes are buried and lithified over geologic time to become fossil dunes. For example, Figure 14.22 shows a rock face in Zion National Park, located on the Colorado Plateau in Utah. The beds in Figure 14.22 appear to be tilted. However, recall from the discussion above that sedimentary rocks on the Colorado Plateau are mostly flat-lying. In this case, the steep layers of sandstone were not produced by tectonic tilting but rather across beds that represent the original layers of the dune slip face. The crossbeds dip in the direction that the wind was blowing when it deposited the sand. Notice that the crossbeds in Figure 14.22 dip in different directions. The variety of dip directions results in part from the curved shape of each crossbed surface within the dune. Each crossbed surface is curved because it is the lithified slip face of the original dune which itself was curved. In addition, however, the variety of dip directions suggests that the wind direction shifted somewhat through time as the ancient sand dunes were being deposited. Lowest wind can carry silt for hundreds or even thousands of kilometers, and then deposit it as loess. Loess generally is composed of silt, is porous, and lacks layering. Even though loess usually is not cemented, it typically forms vertical cliffs and bluffs because the fine sediment particles stick together more than does uncemented sand or gravel. The largest loess deposits in the world, found in central China, cover 800,000 square kilometers and are more than 300 meters thick. The silt was blown from the Gobi and the Taklamakan deserts of Central Asia. The particles stick together so effectively that people have dug caves into the lowest cliffs to make their homes. However, in 1920, a great earthquake caused the cave system to collapse, burying and killing an estimated 100,000 people. Thick loess deposits accumulated in North America during the most recent Pleistocene glacial advance, when continental ice sheets ground bedrock into silt. Streams carried this fine sediment from the melting glaciers and deposited much of it along their banks and floodplains. These environments were cold, windy, and devoid of vegetation, and wind easily picked up and transported the silt, depositing thick layers of loess as far south as Vicksburg, Mississippi. During the Civil War's Battle of Vicksburg, a siege that lasted for over 7 weeks, residents of Vicksburg took shelter from federal bombardment in nearby loess caves. Loess deposits in the United States range from about 1.5 meters to 30 meters thick. Soils formed on loess are generally fertile mollisols that support vast natural grassland ecosystems and make good farmland. Much of the rich soil of the Central Plains of the United States and eastern Washington state formed on loess. Desertification. The Sahara is the largest desert on the planet. South of the Sahara lies the semi-arid Sahel. During the 1960s, unusually heavy rains caused the Sahel to bloom. People expanded their flocks to take advantage of the additional forage. With foreign aid from rich countries, medical attention and sanitation in the area improved, and the human population grew dramatically. Many people predicted a new era of prosperity for the Sahel, but the favorable rains were an anomaly. In the late 1960s and early 1970s, drought destroyed the region. During this period, governments in North Africa began to enforce national borders more strictly, curtailing nomadism. When people settled in specific regions, their flocks grazed the same area throughout the year. Plants did not have time to regenerate, and the hungry animals chewed the grasses down to the roots. Civil and international war brought instability to the region, and famine struck. Reports issued in the 1970s and 1980s claimed that the Sahara was expanding southward into the Sahel at a rate of 5 kilometers per year. Scientists argued that overgrazing, farming, and firewood gathering had caused the desert expansion. This growth of the desert caused by human mismanagement has been called desertification. More recent research has shown that overgrazing a semi-arid region causes land degradation but does not cause a desert to expand. The Sahara desert boundary is clearly visible on satellite photographs as a boundary separating a region of sparse vegetation from one with almost no plants. Researchers plotted changes in the size of the desert by studying satellite photographs taken between 1980 and 1990. As shown in Figure 14.31, the desert expanded when rainfall declined. Thus, decreasing rainfall, not overgrazing, may have been responsible for expansion of the Sahara. A more recent study in 2018 confirmed this conclusion by showing that over the period 1902-2013, the size of the region receiving less than 100 millimeters of rain per year, the official definition of a desert, grew by 16% during the winter and 11% during the summer. For reference, the 16% wintertime increase in the size of the Sahara between 1902 and 2013 exceeds the combined size of Alaska and California. The 2018 study found that during the summer, the rainfall boundary between the southern Sahara and the Sahel expanded southward, whereas in the winter the northern boundary of the Sahara expanded northward. The study also found that over the course of the 20th century, precipitation during the rainy season in the headwaters of the Niger River declined by as much as 25%. Figure 14.32 shows the resulting average monthly declines in stream discharge for a stream monitoring station located in the Niger River headwaters. Similarly, significant drops in rainy season precipitation over the 20th century were observed in the headwaters of the Blue Nile and Congo rivers. Despite these century-long trends, which the authors of the 2018 study ascribed to global warming and associated changes in ocean and atmospheric circulation patterns, massive agricultural aid to the region has led to improved farming and herding practices in some regions. Farmers have learned land management techniques specific to desert environments, which has helped keep the land usable despite fluctuations in rainfall. As a result, thousands of acres of land have been rehabilitated, and millet and sorghum yields have increased significantly. This story reminds us once again that, while a desert ecosystem is created by low rainfall, human management can significantly alter the productivity of the land. Chapter 15, Ocean Basins. The origin of oceans. The primordial Earth, heated by the impacts of colliding planetesimals and the decay of radioactive isotopes, was molten, or near molten. The sky, without an atmosphere, was black. There were no oceans, no life. Today, we consider Earth in terms of 4 spheres: the geosphere, hydrosphere, atmosphere, and biosphere. Each sphere is as different from the others as a rock is different from a flowing stream, a breath of air, or a butterfly. For the moment, let's abandon our view of Earth's 4 spheres and think of only 2 kinds of Earth compounds: compounds that are volatile, or can evaporate rapidly and easily escape into the atmosphere, and compounds that are not. Water is a good example of a volatile compound. Carbon dioxide is another. Most scientists agree that the surface of primordial Earth consisted mainly of rock and partially molten rock and contained few volatile compounds. How, then, did our thick atmosphere, vast oceans, and a global biosphere of living organisms form? For many years, geologists hypothesized that abundant volatiles, including water and carbon dioxide, were trapped within early Earth's interior. This reasoning was based on three observations and inferences. First, cosmogenic models showed that volatiles were evenly dispersed in the cloud of dust, gas, and planetesimals that coalesced to form the planets. It seemed likely that some of those volatiles would have become trapped within Earth as it formed. Second, scientists detected volatiles in modern comets, meteoroids, and asteroids. If volatiles were trapped within the small objects that passed through our neighborhood in space, it seemed logical to infer that they also accumulated in Earth's interior as the original cloud of dust and gas coalesced. Finally, modern volcanic eruptions eject gases and water vapor into the air. Geologists have inferred that these gases originate in the mantle and are remnants of the original volatiles trapped during Earth's formation. Geologists therefore concluded that some of these volatiles escaped during volcanic eruptions early in Earth's history and that they formed the atmosphere and the oceans, and ultimately gave rise to living organisms. Today, many scientists question this conclusion. To understand their questions, let's return to the cloud of dust and gas that coalesced to form the planets. Recall that our region of space heated up as dust, gas, and planetesimals collided to become planets. At the same time, hydrogen fusion began within the Sun and solar energy radiated outward to heat the inner solar system. The newly born Sun also emitted a stream of ions and electrons, called the solar wind, that swept across the inner planets, blowing their volatile compounds into outer regions of the solar system. As a result, most of Earth's volatile compounds essentially boiled off and were swept by the solar wind into the cold outer regions of the solar system. According to a currently popular hypothesis, shortly after our planet formed and lost its volatiles, a Mars-sized object smashed into Earth. The cataclysmic impact blasted through the crust and deep into the mantle, ejecting huge quantities of pulverized rock into orbit. The fragments eventually coalesced to form the Moon. The impact also ejected most of Earth's remaining volatiles with enough velocity that they escaped Earth's gravity and disappeared into space. According to this hypothesis, Earth's surface then was left barren and rocky, with few volatiles either on the surface or in the deep mantle. Thus, Earth's early surface had neither water nor an atmosphere. The hot mantle churned and volcanic eruptions repaved the planet with lava, but these events brought relatively few volatiles to Earth's surface. According to one estimate, outgassing of the deep mantle accounted for no more than 10% of Earth's hydrosphere, atmosphere, and biosphere. If this scenario is correct, why do modern volcanoes release volatiles? According to one hypothesis, most of the gases given off by modern volcanoes are recycled from the surface. Water, carbon, and other light compounds are carried into shallow parts of the mantle by subducting plates. There, the volatiles are incorporated into magma that forms within the volcanic arc associated with the subduction zone. The volatiles are returned to the surface when volcanoes forming the arc erupt. Thus, modern volcanic eruptions, like their primordial ancestors, do not deliver significant quantities of volatiles from the deep mantle to Earth's surface. Now let's return to the volatiles that streamed away from the hot, inner solar system. As they flew away from the Sun, volatiles entered a cooler region beyond Mars. Most of the volatiles were captured by the outer planets, Jupiter, Saturn, Uranus, and Neptune, but some continued their journey toward the outer fringe of the solar system. There, beyond the orbits of the known planets, volatiles from the inner solar system combined with residual dust and gas to form comets. A comet's nucleus has been compared to a dirty snowball because it is composed mainly of ice and rock. However, other compounds not common in snowballs exist in comets as well. These include frozen carbon dioxide, ammonia, and simple organic molecules. Volatiles are also abundant in certain types of meteoroids and asteroids in the region between Mars and Jupiter. Astronomers calculate that the early solar system was crowded with comets, meteoroids, and asteroids, space debris left over from planetary formation. Much of this material contained volatile compounds. When a large piece of space debris crashes into a planet, it is called a bolide. Early in the formation of the solar system, a large number of bolides crashed into Earth, nearby planets, and moons. In this way, the bolides delivered and deposited a large mass of volatile compounds to the inner solar system. While falling space debris added less than 1% to Earth's total mass, it imported roughly 90% of its modern reservoir of volatiles. Upon entry and impact, the frozen volatiles in the bolides vaporized, releasing water vapor, carbon dioxide, ammonia, simple organic molecules, and other volatile compounds. As the planet cooled and atmospheric pressure increased, the water vapor condensed to liquid, forming the first oceans. The light molecules transported to Earth in bolides also provided gases that formed the atmosphere and the raw materials for life. Thus, at least some, and probably most, of the compounds necessary to produce the hydrosphere, the atmosphere, and the biosphere traveled to Earth from outer regions of the solar system. The water that fills Earth's oceans came from interplanetary space. Later in Earth's history, impacts from outer space blasted rock and dust into the sky, causing mass extinctions and killing large portions of life on Earth. Ironically, extraterrestrial impacts may have provided the raw materials for the oceans, the atmosphere, and for life, but they later caused mass extinctions. The Earth's oceans, if you were to ask most people to describe the difference between a continent and an ocean, they would almost certainly reply, why, obviously, a continent is land and an ocean is water. This observation is true, of course, but to a geologist what is more important is that the rock beneath the ocean water is different from the rock beneath the land surface. The accumulation of seawater in the world's ocean basins is a result of that rock difference. Modern oceanic crust is dense basalt and varies from 4 to 7 kilometers thick. Continental crust is made of lower density granite and averages 20 to 40 kilometers in thickness. In addition, the entire continental lithosphere is both thicker and less dense than oceanic lithosphere. As a result of these differences, the thick, lower-density continental lithosphere floats isostatically at high elevations, whereas oceanic lithosphere sinks to low elevations. Most of Earth's water flows downhill, to collect in the vast depressions formed by oceanic lithosphere. Even if no water existed on Earth's surface, oceanic crust would form deep basins and continental crust would form regions of higher elevation. Oceans cover about 71% of Earth's surface. The seafloor is about 5 kilometers deep in the central parts of the ocean basins, although it is only 2 to 3 kilometers deep above the mid-oceanic ridge and plunges to 11 kilometers in the Mariana Trench. The ocean basins contain 1.4 billion cubic kilometers of water, 18 times more than the volume of all land above sea level. So much water exists at Earth's surface that if Earth were a perfectly smooth sphere, it would be covered by a global ocean 2,000 meters deep. The size and shape of Earth's ocean basins have changed over geologic time. At present, the Atlantic Ocean is growing wider at a rate of a few centimeters each year as the seafloor spreads apart at the mid-Atlantic ridge and as the Americas move away from Europe and Africa. At the same time, the Pacific is shrinking at a similar rate, as oceanic crust sinks into subduction zones around its edges. In short, the Atlantic Ocean basin is now expanding at the expense of the Pacific. Global climate is profoundly influenced by the immense volume of Earth's oceans and the fact that the oceans consist of liquid water. On average, the ocean is about 3,800 meters deep, yet the thermal capacity of Earth's entire atmosphere is equivalent only to the uppermost 2.5 meters of ocean water. Ocean currents transport heat from the equator toward the poles, cooling equatorial climates and warming polar environments. The seas also absorb and store solar heat more efficiently than do rocks and soil. As a result, oceans are commonly warmer in winter and cooler in summer than adjacent land is. Most of the water that falls as rain or snow is water that evaporated from the seas. In these and other ways, the oceans have played a major role in controlling Earth's climate and the distribution of different climate zones through geologic time. Studying the seafloor 75 years ago, scientists had better maps of the moon than of the seafloor. The moon is clearly visible in the night sky, and we can view its surface with a telescope. The seafloor, however, is deep, dark, and inhospitable to humans. Modern oceanographers use a variety of techniques to study the seafloor, including several types of sampling and remote sensing. Sampling. Several devices collect sediment and rock directly from the ocean floor. A rock dredge is an open-mouthed steel net dragged along the seafloor behind a research ship. The dredge breaks rocks from submarine outcrops and hauls them to the surface along with whatever other sediment and biota might be scooped up. Oceanographers sample seafloor mud by lowering a piston coring device to the bottom. This device consists of a steel core barrel with a sharp bit on the lower end, removable plastic tubing that fits inside the hollow core barrel, a large weight attached to the top of the barrel, and a trigger and piston mechanism. The trigger is released when the tip of the core barrel is only a meter or two above the seafloor, allowing the weighted core barrel to freefall to the bottom, where it plunges bit first into the mud. As the weight drives the core barrel downward, the piston inside the tubing is simultaneously drawn upward by a cable, in order to make way for and suck in the mud core. Once the barrel has stopped settling into the mud, the entire device is yanked out of the bottom sediments, winched to the surface, and brought on board. There, scientists extracted, split, and described the core. Because piston coring involves driving the core barrel downward into the mud in one swift action, the length of the core itself is always limited by the strength of the barrel and its ability to penetrate downward into the sediment rather than fold over as the weight drives it downward. Most piston cores are not over 10 meters long. In contrast, seafloor drilling methods developed for oil exploration can recover continuous cores from seafloor sediment as well as lithified rock that are hundreds of meters long. Large drill rigs are mounted on offshore platforms and on research vessels. The drill cuts cylindrical cores from sediment and rock, which are then brought to the surface for study. Remote sensing. Remote sensing methods do not require direct physical contact with the ocean floor, and for some studies this approach is both effective and economical. The echo sounder is an instrument commonly used to map seafloor topography. It emits a sound signal from a research ship and then records the signal after it bounces off the seafloor and travels back up to the ship. The water depth is calculated from the time required for the sound to make the round trip. A topographic map of the seafloor is constructed as the ship steers a carefully navigated course with the echo sounder operating continuously. Modern echo sounders, called sonar, transmit 1,000 signals at a time to create more complete and accurate maps. A seismic reflection profiler works in the same way but uses a higher energy signal that penetrates and reflects from layers of sediment and rock below the seafloor. This geophysical technique provides an image of the layering and structure of seafloor sediments, the rock layers and crust below, and major structures such as folds and faults that might be present. Figure 15. 10 is an example of a modern seismic reflection profile that was shot by the USGS in shallow water off the coast of Central California. The red and blue layers in the image represent layers of sediment and sedimentary rock below the seafloor. Notice the presence of two major strike-slip fault zones, associated with the transform plate boundary between the North American and Pacific plates. A different type of remote sensing that involves the reflection of compression waves off the seafloor is side-scan sonar imaging. This technique involves towing a heavy, torpedo-shaped vessel called a towfish behind a powerful ship. Inside the towfish is an array of transducers that emit, then receive, an acoustic pulse of energy of a specific frequency. Figure 15. 11A is a cartoon showing a towfish emitting and receiving sonar information as it is being towed behind the research ship. Notice that the zone through which the acoustic pulse is sent and received is very narrow in the towing direction but very wide in the direction perpendicular to the towing track. This configuration is designed to maximize the return of sonar energy along the seafloor. As the ship travels and the towfish sends and receives sonar pulses with this configuration, an image called a sonogram is stitched together showing the topography along the seafloor. Rougher areas return more sonar energy and so are bright on the sonogram, whereas smooth areas or shadows result in little sonar energy return and so are darker on the sonogram. Very similar to side scan, sonar imaging is multi-beam imaging. Instead of involving a towfish, multi-beam imaging systems are mounted directly next to the hull of the research vessel. Multiple frequencies of acoustic sonar beams are emitted and received, and the resulting signal is processed on board and shows the topographic information directly below the ship as it moves. A major advantage of the multi-beam system is that bubbles that form in the wake of the ship do not affect the sonar sending and receiving system because it is not being towed behind the ship. A magnetometer is an instrument that measures a magnetic field. Magnetometers towed behind research ships measure the magnetism of seafloor sediment and rock. Data collected by shipborne magnetometers resulted in the now famous discovery of symmetric magnetic stripes on the seafloor. That discovery rapidly led to the development of the seafloor spreading hypothesis and of the theory of plate tectonics shortly thereafter, as described in Chapter 6. Satellite-based microwave radar instruments measure the echo of microwave pulses to detect subtle swells and depressions on the sea surface. These features reflect seafloor topography. For example, the mass of a seafloor mountain 4,000 meters high creates sufficient gravitational attraction to produce a gentle 6-meter high swell on the sea surface directly above it. the microwave data are used to make. Seafloor maps. Features of the seafloor. The Mid-Oceanic Ridge System. The discovery of the Mid-Oceanic Ridge System took place over the course of several decades and was possible only by scientific analysis of large volumes of oceanographic data, much of which was collected for military purposes. Following World War I, oceanographers began using early versions of echo-sounding devices to measure ocean depths. Those surveys showed that the seafloor was much more rugged than previously thought, and they further identified the continuity and size of the Mid-Atlantic Ridge. During World War II, naval commanders needed topographic maps of the seafloor to support submarine warfare. Those detailed maps, made with early versions of the echo sounder, were kept secret by the military. When they became available to the public after peace was restored, scientists were surprised to learn that the ocean floor has at least as much topographic diversity and relief as the continents do. Broad plains, high peaks, and deep valleys form a varied and fascinating submarine landscape. In the 1950s, oceanographic surveys conducted by several nations led to the discovery that the Mid-Atlantic Ridge is just part of a great submarine mountain range, now called the Mid-Oceanic Ridge System. Recall from Chapter 6 that the Mid-Oceanic Ridge System is a continuous submarine mountain chain formed by the rifting apart of two oceanic plates. The Mid-Ocean Ridge System encircles the globe and has a total length exceeding 80,000 kilometers. In some places it is more than 1,500 kilometers wide. The ridge system rises an average of 2 to 3 kilometers above the surrounding deep seafloor because heat from the rifting causes rocks in and around the plate boundary to be hot. The hot rocks of the ridge system take up more volume, so float higher in the underlying asthenosphere. Although the mid-ocean ridge lies almost exclusively beneath the sea surface, it is Earth's longest continuous mountain chain. A rift valley is an elongated depression that develops at a divergent plate boundary. In the Mid-Oceanic Ridge System, a rift valley 1 to 2 kilometers deep and several kilometers wide splits many segments of the ridge crest. Oceanographers in small research submarines have dived into the rift valley, where they have documented gaping vertical cracks up to 3 meters wide on the valley floor. In some cases, extremely hot hydrothermal water highly concentrated with dissolved metals and metal-bearing compounds streams out of the cracks. To understand the geologic significance of such cracks, recall that the Mid-Oceanic Ridge System is a spreading center, where two lithospheric plates are moving apart from each other. The cracks form as tensile stress at the ridge axis causes brittle oceanic crust to separate. Basaltic magma then rises through the resulting crack and flows onto the floor of the rift valley. This basalt becomes new oceanic crust as two lithospheric plates spread outward from the ridge axis. The new crust at the ridge axis is warmer, and therefore of relatively lower density, than older crust and lithosphere located farther from the ridge axis. Its buoyancy causes it to float high above the surrounding seafloor, elevating the Mid-Oceanic Ridge System 2 to 3 kilometers above the deep seafloor. The new lithosphere cools as it spreads away from the ridge. As a result of cooling, the lithosphere shrinks and cracks as it becomes denser and sinks to lower elevations, forming the normal faults, and shallow earthquakes are common along the Mid-Oceanic Ridge System because oceanic crust fractures as the two plates separate. Blocks of crust drop downward along some of the seafloor cracks, forming faults that bound the rift valley. Thus, the cracks documented along the mid-ocean spreading ridge by oceanographers can be explained as the result of three primary causes: separation of rock by tectonic tension associated with the spreading ridge, decrease of rock volume by the cooling and contraction of newly formed basalt crust on the ocean floor, and normal faulting in which rock is physically displaced across a crack. On the volcanically active Mid-Oceanic Ridge System, hot rocks heat seawater as it circulates through fractures in oceanic crust. The hot water dissolves metals and sulfur from the rocks. Eventually, the hot metal and sulfur-laden water rises back to the seafloor surface, spouting from fractures as a jet of cloudy, black water called a black smoker. The black color is caused by precipitation of fine-grained metal sulfide minerals as the solutions cool on contact with seawater. These scalding, sulfurous waters are as hot as 400 degrees Celsius, and seemingly would produce a sterile environment in which nothing could survive. Yet, remarkably, the deep seafloor around a black smoker teems with life. At the vents, bacteria produce energy from hydrogen sulfide in a process called chemosynthesis. Thus, the bacteria release energy from chemicals and are not dependent on photosynthesis. The chemosynthetic bacteria are the foundation of a deep-sea food chain, Either larger vent organisms eat them or the larger organisms live symbiotically with the bacteria. For example, instead of a digestive tract, the red-tipped tube worm has a special organ that hosts the chemosynthetic bacteria. In return for providing a home for the bacteria, the worm receives nutrition from the bacteria's wastes. Other vent organisms in this unique food chain include giant clams and mussels, eyeless shrimp, crabs, and fish. In addition to cracks or faults located along the axis of the midoceanic ridges and rift valleys are hundreds of fractures, called transform faults, that cut across the rift valleys and ridges. These fractures extend through the entire thickness of the lithosphere and develop because the midoceanic ridge system consists of many short segments. Each segment is slightly offset from adjacent segments by a transform fault. Transform faults are original features of the midoceanic ridge. They form as an accommodation to Earth's spherical shape when lithospheric spreading begins. Some transform faults displace the ridge by less than a kilometer, but others offset the ridge by hundreds of kilometers in some cases. A transform fault can grow so large that it forms a transform plate boundary. The San Andreas Fault in California is a transform plate boundary that offsets both global sea level changes and the midoceanic ridge system. Thin layer of marine sedimentary rocks blankets large areas of Earth's continents. These rocks tell us that those places must have been below sea level when the sediment accumulated. Tectonic activity can cause a continent to sink, allowing the sea to flood a large area. However, at particular times in the past, marine sediments accumulated on low-lying portions of all continents simultaneously, indicating simultaneous global flooding of low-elevation regions on all continents. Although our plate tectonics model explains the sinking of individual continents, or parts of continents, it does not explain why all continents should sink at the same time. Therefore, we need to explain how sea level could rise globally by hundreds of meters to flood all continents simultaneously. Continental glaciers have advanced and melted numerous times in Earth's history. During the growth of continental glaciers, seawater evaporates and is frozen into the ice that rests on land. As a result, sea level drops. When glaciers melt, the water runs back into the oceans and sea level rises. The alternating growth and melting of glaciers during the Pleistocene epoch caused sea level to fluctuate by as much as 150 meters. However, the ages of most marine sedimentary rocks on continents do not coincide with times of glacial melting. Therefore, we must look for a different cause to explain continental flooding. Recall that the new, hot lithosphere at a spreading center is buoyant, causing the midoceanic ridge system to rise above the surrounding seafloor. This submarine mountain chain displaces a huge volume of seawater. If the midoceanic ridge system were smaller, it would displace less seawater and sea level would fall. If it were larger, sea level would rise. The midoceanic ridge rises highest at the spreading center, where new lithosphere rock is hottest and has the lowest density. The elevation of the ridge decreases on both sides of the spreading center because the lithosphere cools and shrinks as it moves outward. Now consider a spreading center where spreading is very slow. At such a slow rate, the newly formed lithosphere LD cool before it migrated far from the spreading center. As a result, the ridge would be narrow and of low volume, as shown in Figure 15.19a. In contrast, rapid seafloor spreading of 10 to 20 centimeters per year would create a high-volume ridge because the newly formed hot lithosphere would be carried a considerable distance away from the spreading center before it cooled and shrank. This high-volume ridge would displace considerably more seawater than would a low-volume ridge, and the high-volume ridge would cause global sea level to rise. To summarize, rapid spreading produces a larger volume of hot rock and pushes aside more seawater, causing global sea level to go up. If spreading then slows down, a smaller volume of hot rock is produced, displacing less seawater and causing global sea level to fall. Seafloor age data indicate that the rate of seafloor spreading has varied from about 2 to 16 centimeters per year over the past 200 million years ago, since the Jurassic period. During late Cretaceous times, between 110 and 85 million years ago, seafloor spreading was unusually rapid, and that rapid spreading caused the formation of an unusually high-volume midoceanic ridge. As the total volume of the midoceanic ridge grew with the increase in average global spreading rate, more and more seawater was displaced and low-lying portions of continents were inundated. Geologists have found marine sedimentary rocks of late Cretaceous age on nearly all continents, indicating that late Cretaceous time was, in fact, one of abnormally high global sea level. Thus, a process initiated by heat transfer deep within the geosphere profoundly affected the sea level of the hydrosphere and life throughout the biosphere. Unfortunately, because no oceanic crust is older than about 200 million years, the specific relationships between seafloor spreading rates and global sea level cannot be tested for earlier times when extensive marine sedimentary rocks accumulated on continents, oceanic trenches and island arcs in many parts of the Pacific Ocean, and in some other ocean basins. Two oceanic plates converge. One dives beneath the other, forming a subduction zone. The sinking plate pulls the seafloor downward, forming a long, narrow depression called an oceanic trench. The deepest place on Earth is in the Mariana Trench, north of New Guinea in the southwestern Pacific, where the ocean floor is nearly 11 kilometers below sea level. Depths of 8 to 10 kilometers are common in other trenches. Huge amounts of magma are generated in the subduction zone. The magma rises and erupts at the seafloor to form submarine volcanoes next to the trench. The volcanoes eventually grow to become a chain of islands called an island arc, as we learned in Chapter 9. The Western Aleutian Islands are an example of an island arc. Many others occur at the numerous convergent plate boundaries in the Western Pacific. If subduction stops after an island arc forms, volcanic activity also ends. The island arc may then ride passively along with another tectonic plate until it arrives at another subduction zone. However, the density of island arc rocks is relatively low, making them too buoyant to sink into the mantle. Instead, the island arc is mashed against the side of the overriding plate. When an island arc and continent begin to slowly mash together, or collide, the subducting plate commonly fractures on the seaward side of the island arc to form a new subduction zone. In this way, the island arc breaks away from the ocean plate and becomes part of the continent, enlarging it. Much of the crust now underlying Western California, Oregon, Washington, and western British Columbia was added to North America in this way between 180 million and about 50 million years ago, when several island arcs formerly in the eastern Pacific Ocean slowly collided with the western margin of the North American plate. A simplified geologic map of these late additions to the North American continent, in general called accreted terrains, is shown in Figure 15.23. Seamounts, oceanic islands, and atolls. A seamount is a submarine mountain that rises 1 kilometer or more above the surrounding seafloor. An oceanic island is a seamount that rises above sea level. Both are common in all ocean basins but are particularly abundant in the southwestern Pacific Ocean. Seamounts and oceanic islands sometimes occur as isolated peaks, but they are more commonly found in chains. Dredge samples show that seamounts, oceanic islands, and the ocean floor itself are all made of basalt. Many seamounts and oceanic islands are volcanoes that formed at a hot spot above a mantle plume, and most form within a tectonic plate rather than at a plate boundary. An isolated seamount or short chain of small seamounts probably formed over a plume that lasted for only a short time. In contrast, a long chain of large islands, such as the Hawaiian Island Emperor Seamount Chain, formed over a long-lasting plume. In this case, the lithospheric plate migrated over the plume as the magma continued to rise from a source beneath the lithosphere. Each volcano formed directly over the plume and then became extinct as the moving plate carried it away from the plume. As a result, the seamounts and oceanic islands become progressively younger toward the island of Hawaii, located at the end of the chain and currently located over the active mantle plume. After a volcanic island forms, it begins to sink, or subside. 3. Factors contribute to the sinking. 1. If the mantle plume stops rising, it stops producing magma. Then the lithosphere beneath the island cools and becomes denser, and the island sinks. Alternatively, a moving plate may carry the island away from the hot spot. This also results in the cooling, contraction, and sinking of the island. 2. The weight of the newly formed volcano causes isostatic sinking. 3. Erosion lowers the top of the volcano. These three factors gradually transform a volcanic island to a seamount over geologic time. Calculations suggest that if the Pacific Ocean plate continues to move at its present rate, the island of Hawaii may sink beneath the sea within 10 to 15 million years. In this case, sea waves likely will erode a horizontal upper surface on the sinking island, forming a flat-topped seamount called a guyot, as illustrated in Figure 15.26. The South Pacific and portions of the Indian Ocean are dotted with numerous other islands called atolls. An atoll is a circular coral reef that forms a ring of islands around a central lagoon. Atolls vary from 1 to 130 kilometers in diameter and are surrounded by the deep water of the open sea. If corals live only in shallow water, how did atolls form in the deep sea? Charles Darwin studied this question during his famous voyage on the Beagle from 1831 to 1836. He reasoned that a coral reef must have formed in shallow water on the flanks of a volcanic island. Eventually the island sank, but the reef continued to grow upward, so that the living portion always remained in shallow water. This proposal was not accepted at first because scientists could not explain how a volcanic island could sink. However, when scientists drilled into a Pacific atoll shortly after World War II and found volcanic rock hundreds of meters beneath the reef, Darwin's hypothesis was revived. It is considered accurate today, in light of our ability to explain why volcanic islands sink. Sediment and rocks of the seafloor. Early oceanographers had believed that the oceans are 4 billion years old, so mud on the ancient seafloor should have been very thick, having had so much time to accumulate. In 1947, however, scientists on the U.S. research ship Atlantis discovered that the mud layer on the bottom of the Atlantic Ocean is much thinner than they expected. Why is there so little mud on the seafloor? The answer to this question would be a crucial piece of evidence in the development of the theory of plate tectonics. Earth is 4.6 billion years old, and rocks as old as 4.04 billion years have been found on the North American continent. Because of its buoyancy, most continental crust remains near Earth's surface. In contrast, no parts of the seafloor are older than about 200 million years, because oceanic crust forms continuously at the mid-oceanic ridge and then recycles into the mantle at subduction zones. As the theory of plate tectonics was emerging in the early 1960s, it became apparent that the presence of only a thin layer of mud covering the oceanic crust could be easily explained if the oldest seafloor is less than 200 million years old, not 4 billion years old as oceanographers had once advocated. This evidence supported the fledgling plate tectonics theory in its early days. Seismic reflection profiling and seafloor drilling show that oceanic crust is made of 3 layers. The uppermost layer consists of sediment, and the lower 2 are basalt. Ocean floor sediment. The uppermost layer of oceanic crust consists of 2 types of sediment. Terrigenous sediment is sand, silt, and clay eroded from the continents and delivered to deep water mainly through submarine canyons that extend outward from the continental shelf. Thus, most terrigenous sediment is found close to the continents. Pelagic sediment, however, collects even on the deep seafloor far from continents. It is a gray and red-brown mixture of silt and clay-sized particles that were transported by wind as dust derived from continental weathering and that lived in the ocean surface waters as sand-sized and smaller phytoplankton that photosynthesized, died, and sank. Pelagic sediment accumulates at a rate of about 2 to 10 millimeters per 1,000 years. Near the mid-oceanic ridge system there is very little to virtually no sediment because the seafloor is so young. The sediment thickness increases with distance from the ridge because the seafloor becomes older as it spreads away from the ridge and, consequently, the sediment has had more time to accumulate. Close to shore, pelagic sediment becomes diluted by more and more terrigenous sediment, forming accumulations that can exceed 10 kilometers in thickness, though more typically are around 4 kilometers in thickness. The observation that the thickness of seafloor mud increased with distance from the ridge also supported the plate tectonics theory in its early days. Parts of the ocean floor beyond the mid-oceanic ridge system are flat, level, essentially featureless surfaces called the abyssal plains. They are the flattest surfaces on Earth. Seismic profiling shows that the basaltic crust is rough and jagged throughout the ocean. On the abyssal plains, however, pelagic sediment buries this rugged surface, forming smooth surfaces. If you were to remove all of the sediment, you would see rugged topography similar to that of the mid-oceanic ridge. Basaltic oceanic crust below the superficial layer of sediment on the ocean floor is a layer of basalt about 1 to 2 kilometers thick. It consists mostly of pillow basalt, which forms as hot magma oozes onto the seafloor. Contact with cold seawater causes newly erupting molten lava to rapidly form a solidified outer rind. Still molten and pressurized magma immediately below the rind causes it to deform plastically into bulbous, pillow-shaped spheroids, called pillows. Beneath the pillow basalt is the deepest and thickest layer of oceanic crust, consisting of between 3 and 5 kilometers of basalt that did not erupt onto the seafloor. This basalt directly overlies the mantle. The upper portion consists of vertical basalt dikes that formed as basaltic magma oozing toward the surface froze in the cracks of the Rift Valley. The lower portion consists of gabbro, the coarse-grained equivalent of basalt. The gabbro forms as pools of magma cool slowly, insulated by the basalt dikes above them. The pillow basalt, vertical basalt dikes, and gabbro all form at the mid-oceanic ridge. These rocks make up the foundation of all oceanic crust because all oceanic crust forms at a ridge axis and then spreads outward. In some places, chemical reactions with seawater have altered the basalt to a soft, green rock called serpentinite that contains up to 13% water. Serpentinite is a fairly common rock type in parts of California and the Pacific Northwest due to the presence of abundant basalt and altered basalt that represents oceanic crust associated with the accreted terrains found there. Superb outcrops of serpentinite are found on U.S. Highway 1 south of Big Sur, California, figure 15.32. Continental margins. A continental margin is a place where continental lithosphere meets oceanic lithosphere. Two types of continental margins exist. A passive continental margin occurs where continental and oceanic lithosphere are firmly joined together. Because it is not a plate boundary, little tectonic activity occurs at a passive margin. Continental margins on both sides of the Atlantic Ocean are passive margins. In contrast, an active continental margin occurs at a convergent plate boundary, where oceanic lithosphere sinks beneath the continent in a subduction zone. The west coast of South America is an active continental margin, also called an Andean margin, as you learned in Chapter 9. Passive continental margins. Recall from Chapter 6 that about 250 million years ago all of Earth's continents were joined into the supercontinent called Pangaea. Shortly thereafter, Pangaea began to rift apart into the continents as we know them today. The Atlantic Ocean opened as the east coast of North America separated from Europe and Africa. As Pangaea broke up, the continental crust fractured and thinned near the fractures. Basaltic magma rose at the new spreading center, forming oceanic crust between North America and Africa. All tectonic activity then focused on the continually spreading mid-Atlantic ridge, and no further tectonic activity occurred at the continental margins, hence the term passive continental margin, figure 15.33c. The continental shelf on all continents, streams, and rivers deposit sediment in coastal deltas such as the Mississippi Delta. Much of this sediment is redistributed along the coastline by ocean currents and downslope as sediment gravity flows, mixtures of sediment and water that flow downslope as a fluid, usually as a bottom-hugging current. Much of the sediment transported downslope from the shoreline and offshore forms a shallow, gently sloping underwater surface that marks the edge of the continent and is called a continental shelf. As sediment accumulates on a continental shelf, the edge of the continent sinks isostatically because of the added weight. This effect keeps the shelf generally below sea level. At the same time, the delivery and accumulation of more sediment from the weathering of the nearby continent causes the outer edge of the continental shelf to build outward, ultimately enlarging the size of the continent itself. In this way, mass is redistributed from the continental interior, where mountains are eroded, to the continental margins, which actively grow outward due to the accumulation of sediment there. Over millions of years, several kilometers of sediment accumulated on the passive east coast of North America, forming a broad continental shelf that projects outward along the entire coast. Beginning at the shoreline, the water depth of the North American Atlantic shelf increases gradually to about 200 meters at the outer shelf edge, which in most places is over 100 kilometers offshore. The average inclination of the continental shelf over this distance is about 0.1 degree. A continental shelf on a passive margin can be a very large feature. The shelf off the coast of southeastern Canada is about 500 kilometers wide, and parts of the shelves of Siberia and northwestern Europe are even wider. In some places, a supply of sediment may be lacking, either because no rivers bring sand, silt, or clay to the shelf or because ocean currents do not deliver sediment to the particular region. In warm regions where terrigenous sediment is either lacking or is delivered in very small quantities, carbonate reef-building organisms such as corals, mollusks, bryozoa, calcareous algae, and numerous others can thrive. When environmental conditions are optimal, the carbonate-generating ecosystem can produce very large volumes of carbonate sediment in very short periods of time. As a result, in tropical and subtropical latitudes where the rate of clastic sediment is low enough and water temperature and salinity is optimal, thick beds of limestone can accumulate. Limestone accumulations of this type may be hundreds of meters thick and hundreds of kilometers across and are called carbonate platforms. The Florida Keys and the Bahamas are modern-day examples of carbonate platforms on continental shelves. Some of the world's richest petroleum reserves occur on the continental shelves of the North Sea between England and Scandinavia, in the Gulf of Mexico, and in the Beaufort Sea on the northern coast of Alaska and western Canada. In recent years, oil companies have explored and developed these offshore reserves. Deep drilling has revealed that granitic continental crust lies beneath the sedimentary rocks, confirming that the continental shelves are truly parts of the continents despite the fact that they are covered by seawater. The continental slope and rise at the outer edge of a shelf, the seafloor gradually steepens to an average slope of about 3 degrees, though. It can vary from 1 degree to 10 degrees, as it increases in depth from 200 meters to about 3 kilometers. This steep region of the seafloor averages about 50 kilometers wide and is called the continental slope. It is a surface formed by sediment accumulation, much like the shelf. Its steeper angle is due primarily to thinning of continental crust where it nears the junction with oceanic crust. Offshore seismic reflection profiling shows that the sedimentary layering is commonly disrupted where sediment has slumped and slid down the steep incline. A continental slope becomes less steep as it gradually merges with the deep ocean floor. This region, called the continental rise, consists of an apron of terrigenous sediment that was transported across the continental shelf and deposited on the deep ocean floor at the foot of the slope. The continental rise averages a few hundred kilometers wide. Typically, it joins the deep seafloor at a depth of about 5 kilometers. In essence, then, the shelf slope rise complex is a smoothly sloping, submarine surface on the edge of a continent formed by accumulation of sediment eroded from the continent. Submarine canyons and submarine fans in many places, seafloor maps show deep valleys, called submarine canyons, eroded into the continental shelf and slope. They look like submarine stream valleys. A canyon typically starts on the outer edge of a continental shelf, usually beyond the outer reaches of a major river delta on the inner shelf, and continues across the slope to the rise. At its lower end, a submarine canyon commonly leads into a submarine fan. A large, fan-shaped accumulation of terrigenous sediment delivered down the submarine canyon to the continental rise by sediment. Gravity flows. Most submarine canyons occur downslope of a region where large rivers enter the sea. When they were first discovered, geologists thought the canyons had been eroded by rivers during the Pleistocene epoch, when accumulation of glacial ice on land lowered sea level by as much as 150 meters. However, this explanation cannot account for the deeper portions of submarine canyons that cut erosionally into the lower continental slopes at depths of a kilometer or more. These deeper parts of the submarine canyons must have formed through erosion, and a submarine mechanism must be found to explain them. Geologists subsequently discovered that sediment gravity flows, underwater mixtures of sediment and water that flow downslope, can erode the continental shelf and slope to create or deepen the submarine canyons. Particularly efficient at eroding rock and sediment underwater are turbidity currents, a form of sediment gravity flow in which a turbulent mixture of sediment and seawater that is more dense than the seawater alone and so flows downslope along the bottom. You can create and observe a turbidity current at home by slowly pouring a cup of muddy water into a sloping basin of clear water. Turbidity currents can be triggered by an earthquake, a large storm, or simply by the oversteepening of the slope as sediment accumulates. When the sediment starts to move, it mixes with water and flows across the shelf and down the slope as a turbulent, chaotic fluid. A turbidity current can travel at speeds greater than 100 km per hour and for distances in excess of 1,200 km. Sediment-laden water traveling at such speed has tremendous erosive power. Once a turbidity current cuts a small channel into the shelf and slope, subsequent currents follow the same channel, just as a stream uses the same channel year after year. Over time, the currents erode a deep submarine canyon into the shelf and slope. Turbidity currents slow down when they reach the deep seafloor. The sediment accumulates there to form a submarine fan. Most submarine canyons and fans form near the mouths of large rivers because the rivers supply the great amount of sediment needed to create turbidity currents and other types of sediment gravity flows. Most of the largest submarine fans form on passive continental margins. Submarine fans that form on active margins typically are much smaller because the trench swallows much of the sediment. Furthermore, most of the world's largest rivers drain toward passive margins. The largest known fan is the Bengal fan, which covers about 4 million square kilometers beyond the mouth of the Ganges River in the Indian Ocean east of India. More than half of the sediment eroded from the rapidly rising Himalayas ends up in this fan. Interestingly, the Bengal Fen has no associated submarine canyon, perhaps because the sediment supply is so great that the rapid accumulation of sediment prevents erosion of a canyon. Active continental margins form along Andean style subduction zones, where an oceanic plate converges with a continent, and along less common transform plate boundaries where oceanic crust is sliding past continental crust, as with the San Andreas Fault in California. In convergent margins, most of the sediment transported from a continent is swallowed up in the trench. As a result, an active margin commonly has a narrow continental shelf or none at all. The landward wall of the trench is the continental slope of an active margin. It typically inclines at 4 degrees or 5 degrees in its upper part and steepens to 15 degrees or more near the bottom of the trench. The continental rise is absent or relatively small because sediment gravity flows generally transport sediment into the trench instead of across it to the ocean floor located over subducting plate. Note that a trench can form wherever subduction occurs, where oceanic crust sinks beneath the edge of a continent, or where it sinks beneath another oceanic plate. However, the trench will be associated with a continental margin only when the overriding plate is made of continental lithosphere. At convergent boundaries, the oceanic plate sinks into the mantle at descent angles ranging from about 15 degrees to beyond vertical. Regardless of this remarkably wide variation in the descent angle of subducting slabs around Earth's ocean basins, an ocean trench is formed, although in some regions the trench is filled with sediment and is not as obvious as elsewhere. For example, offshore of the Pacific Northwest, the Juan de Fuca plate is subducting below the North America plate, but the subduction is filled with sediment resulting from draining of the Cascades and Northern Rockies. The Columbia River has been the largest deliverer of sediment to the trench, as huge volumes of water and sediment poured out of the Columbia River during and following each glaciation over the past 3 million years or so. In contrast, the Marianas Trench off the eastern coast of the Philippines includes Earth's deepest ocean depth at 10,994 kilometers, 6.8 miles. Chapter 16, Oceans and Coastlines. Introduction. About 60% of the world's human population lives within 100 kilometers of the coast. 1 million people live on low coral islands, and many millions more live on low-lying coastal land vulnerable to coastal flooding. At risk are not just individuals and villages but unique human cultures. Faced with changing coastal environments, these people are threatened with forced abandonment of their nations. Popular media coverage has linked damage along the American Gulf Coast to sea level rise induced by global warming. However, many geologists and oceanographers argue that other factors such as crustal subsidence, described in Chapter 15, may be responsible for the submergence of this region. In a similar manner, several Pacific Island nations risk elimination due to the combined effects of global sea level rise and cooling-related subsidence of the volcanic rock on which they are built. Regardless of the cause of coastal sea level rise, for many people, it is disturbing that solid land should sink beneath the waves or that a modern city such as New York could be rendered nearly defenseless against a major storm, as was the case in 2012 with Hurricane Sandy. Yet geologists know that continents and islands have risen from the sea and sunk back beneath the waves throughout Earth's history, and that, even viewed through the much shorter period of written human history, changes in sea level have directly affected the economic activities of humans living and working near the coast. Figure 16. 1. In this chapter, we will continue studying Earth's oceans, focusing specifically on the processes that form, shape, or destroy islands and coastlines. Coastlines are among the most geologically active environments on Earth. Sea level rises and falls, flooding shallow parts of continents and stranding beaches high above the sea surface. Regions of continental and oceanic crust also rise and sink, with results similar to those caused by fluctuating sea level. Rivers deposit great quantities of sand and mud on coastal deltas. Waves and currents erode beaches and transport sand along hundreds or even thousands of kilometers of shoreline. Converging tectonic plates buckle coastal regions, creating mountain ranges, earthquakes, and volcanic eruptions. Geography of the oceans. All of Earth's oceans are connected, and water flows from one to another, so in one sense, Earth has just one global ocean. However, several distinct ocean basins exist within the global ocean. The largest and deepest is the Pacific. It covers 1/3 of Earth's surface, more than all land combined, and contains more than half of the world's water. The Atlantic Ocean has about half the surface area of the Pacific. The Indian Ocean is slightly smaller than the Atlantic. The Arctic Ocean surrounds the North Pole and extends southward to the shores of North America, Europe, and Asia. Therefore, it is bounded by land, with only a few straits and channels connecting it to the Atlantic and Pacific Oceans. The surface of the Arctic Ocean freezes in winter, and parts of it melt for a few months during summer and early fall. The Antarctic Ocean, feared by sailors for its cold and ferocious winds, has no sharp northern boundary. The northernmost limit of the Antarctic Ocean is the zone where warm currents from the north converge with cold Antarctic water. Seawater salts and trace elements. The salinity of seawater is the total quantity of dissolved salts, expressed as a percentage. In this case, the term salts refers to all dissolved ions, not only sodium and chloride. Dissolved ions make up about 3.5% of the weight of ocean water. The 6 ions listed in Figure 16. 3 make up 99% of the ocean's dissolved compounds. However, almost every other element found on land is also found dissolved in seawater, albeit in trace amounts. For example, seawater contains about 0.00000004% gold. Although the concentration is small, the oceans are large and therefore contain a lot of gold. About 4.4 kilograms of gold is dissolved in each cubic kilometer of seawater. Because the oceans contain about 1.3 billion cubic kilometers of water, about 5.7 billion kilograms of gold exists in the oceans. Unfortunately, it would be hopelessly expensive to extract even a small portion of this amount. The world's rivers carry more than 2.5 billion tons of dissolved salts to the oceans every year. Underwater volcanoes contribute additional dissolved ions. However, the salinity of the oceans has been relatively constant throughout much of geologic time because salt has been removed from seawater at roughly the same rate at which it has been added. When a portion of a marine basin becomes cut off from the open ocean, the water evaporates, precipitating thick sedimentary beds of salt. Additionally, large quantities of salt become incorporated into mudstone and other sedimentary rocks through the precipitation of salt. Minerals within these rocks. Dissolved gases in addition to trace elements and salts. Seawater also contains dissolved gases, especially carbon dioxide and oxygen. These dissolved gases exchange freely and continuously with the atmosphere. If the atmospheric concentration of carbon dioxide or oxygen rises, much of the gas quickly dissolves into seawater. If the atmospheric concentration of a gas falls, that gas exsolves from the sea and enters the atmosphere. Thus, the seas buffer atmospheric concentrations of gases. At the same time, the atmosphere buffers the chemistry of seawater. When carbon dioxide dissolves in seawater, the seawater becomes more acidic. In recent years, increasing concentrations of carbon dioxide gas from the burning of fossil fuels has caused not only the atmosphere and oceans to become warmer but also the seawater to become more acidic. That is, when carbon dioxide dissolves in seawater, it forms carbonic acid. As more CO from the atmosphere diffuses into the oceans and converts to carbonic acid, the pH of the ocean as a whole drops. This process is called ocean acidification. Over the past 28 years, oceanographers have measured a drop in the pH of the oceans from about 8.1 to about 8.0. Although this small change may seem insignificant, the pH scale is not linear, and small drops in pH correspond to large increases in acidity. A pH drop from 8.1 to 8.0 represents an increase in acidity, or the concentration of hydrogen ions, of about 58%. Recent and ongoing ocean acidification has very seriously affected marine ecosystems. Corals, many kinds of algae, shellfish, foraminifera, and other organisms that make hard body parts out of calcium carbonate are particularly hard hit because calcium carbonate dissolves under acidic conditions. As the oceans acidify, these organisms spend more of their metabolic energy trying to precipitate their hard parts and so are stressed. As the acidity increases, eventually a point is reached where the organism cannot maintain its calcium carbonate production and so it dies. Carbonate reef environments are especially negatively affected by recent increases in ocean acidification, and the recent loss of coral reef ecosystems is really alarming. From 2016 to 2018, half of the coral reefs in Australia's Great Barrier Reef died and no longer exist as a reef ecosystem. Left behind are vast underwater thickets of bleached white calcium carbonate skeletons from dead corals. Temperature Recall from Chapter 11 that temperate lakes are comfortably warm for swimming during the summer because warm water floats on the surface and does not readily mix with the deep, cooler water. Much of Earth's oceans develop a similar temperature layering, but because sea waves and currents stir the surface water, the warm layer can extend from the surface to a depth as great as 450 meters. Below this layer is the thermocline, where the temperature drops rapidly with depth. The thermocline extends to a depth of about 2 kilometers beneath the thermocline. The temperature of ocean water varies from about 1 degree Celsius to 2.5 degrees Celsius. The cold, dense water in the ocean depths mixes very little with the surface. Thus, there are 3 distinct temperature zones in the ocean, as shown in Figure 16.7. This layered structure does not exist in the polar seas because cold surface water sinks, causing vertical mixing. Tides even the most casual observer will notice that on any beach the level of the ocean rises and falls on a cyclical basis. If the water level is low at noon, it will reach its maximum height at about 6:13 p.m. and be low again at about 12:26 a.m. These vertical displacements are called tides. Most coastlines experience 2 high tides and 2 low tides during an interval of about 24 hours and 53 minutes. Tides are caused by the gravitational pull of the moon and sun on the sea surface. Although the moon is much smaller than the sun, it is so much closer to Earth that its influence predominates. At any given time, one region of Earth lies directly closest to the moon. Because gravitational force is greater for objects that are closer together, the part of the ocean nearest to the moon is attracted with the strongest force. There, the ocean surface bulges upward toward the moon, forming a tidal bulge. As a particular geographic point on Earth's coastlines rotates underneath a tidal bulge, that coastline experiences a high tide. But so far our explanation is incomplete. As Earth spins on its axis, a given point on Earth passes directly under the moon approximately once every 24 hours and 53 minutes, but the period between successive high tides is only 12 hours and 26 minutes. Why are there ordinarily 2 high tides in a day? The tide is high not only when a point on Earth is directly under the moon but also when it is 180 degrees away. That is, the tidal bulge created by the gravitational effect of the moon has 2 ends. One end faces the moon and one end faces directly opposite the moon on the other side of Earth. To understand how a tidal bulge forms on the side of Earth facing away from the moon, we must consider the Earth-Moon orbital system. Most people visualize the moon orbiting around Earth, but it is more accurate to say that Earth and the moon orbit around a common center of gravity. The 2 celestial partners are locked together like dancers spinning around in each other's arms. Just as the back of a dancer's dress flies outward as she twirls, the ocean surface on the opposite side of Earth from the moon bulges outward. This bulge forms the high tide 180 degrees away from the moon. Thus, the tides rise and fall twice daily. High and low tides do not occur at the same time each day but are delayed by approximately 53 minutes every 24 hours. Earth makes one complete rotation on its axis in 24 hours, but at the same time, the Earth-Moon pair is rotating around its common center of gravity. After a point on Earth makes one complete rotation in 24 hours, that point must continue to rotate for an additional 53 minutes before it catches up with the new position of the moon resulting from rotation of the Earth-Moon pair. This is why the moon rises approximately 53 minutes later each day. In the same manner, the tides are approximately 53 minutes later each day. Although the sun's gravitational pull on the oceans is smaller than the moon's, it does affect tides. When the sun and moon are directly in line with Earth, their gravitational fields combine to create a large tidal bulge. During these times, the variation between high and low tides is large, producing spring tides. When the moon is 90 degrees out of alignment with the sun and Earth, each partially offsets the effect of the other and the differences between the levels of high and low tide are smaller. These relatively small tides are called neap tides. Tidal range is strongly affected by the shape of the coastline. For example, the Bay of Fundy is shaped like a giant funnel. The shape of the bay concentrates the rising and falling tides, and as a result the tidal range is as much as 15 meters during a spring tide. In contrast, tides vary by less than 2 meters along a straight stretch of coast such as that in Santa Barbara, California. In the Central Oceans, the tides average about 1 meter. Mariners consult tide tables that give the time and height of the tides in any area on any day. Sea waves. Most ocean waves develop when wind blows across water. Waves vary from tiny ripples on an otherwise smooth surface to destructive giants that can topple beach houses and sink ships. In deep water, the size of a wave depends on the wind speed, the length of time that the wind has blown, and the distance that the wind has traveled. A 25 km/h wind blowing for 2 to 3 hours across a 15 km wide bay generates waves about 0.5 meters high. But if a storm blows at 90 km/h for several days over a fetch of 3,550 kilometers, it can generate 30-meter-high waves, as tall as a ship's mast. The highest part of a wave is called the crest, the lowest is the trough.